In a previous episode, we were looking at this idea of energy and the first law of thermodynamics that states that energy cannot be created nor destroyed. So the only thing we ever do with energy is we kind of transfer it back and forth. So in this episode, we're going to look at this idea of, well, what exactly is energy and how do we apply and work with energy in chemistry? How do we apply and work with energy when it regards to a chemical reaction or a chemical process? So we're going to be looking at, in this episode, the idea of internal energy, how to describe it, how to quantify it, and how to relate it back to our bigger picture of chemistry. Now, before we go much further, the first thing we want to look at is how do we go about measuring energy? And here's a news flash. We do not use a thermometer. That is always the first instrument everyone wants to yell at. When we talk about energy, remember that energy is a force that is being moved through a distance, right? So energy is the ability to do work. Work is nothing more than a force being moved through a distance. So when we talk about energy, we're going to measure it in the SI system with something known as a joule, Joule. And joules are used to measure, in essence, the amount of energy that gets transferred between one object and another, one reaction and another, the system, the surroundings, however you want to talk about it. Originally, if that word joules doesn't sound very familiar, you probably heard of the original term, which was known as a calorie, right? And when we talk about a calorie was the amount of energy that was required to raise 1 gram of water 1 degree Celsius. Right? Now that was the old, this is a good example of the metric system, right? So that was the old school version of it. Now, for reasons that we will discuss later on, we shifted from a calorie, which was based upon water, to a joule, which is a more universal measurement. But what you need to know for right now is either a calorie or a joule will measure energy. And the relationship between the two of them is that for every 1 calorie, that is going to equal 4.18 joules. Now notice, in none of this did I ever talk about degrees. Because remember, degrees are used to measure temperature. Okay? Temperature is not energy. It's related, but temperature is technically referred to as the average kinetic energy. And that word average is important because that's why it is not a simple matter of I'm not feeling well and I put a thermometer in my mouth. I'm never going to sit there and tell you, oh, I have a fever. Look how many joules I'm at. That's not what we're doing. When we measure temperature, it's an average. That's why it's a degree function. And so when we talk about internal energy, it is a little hard to describe internal energy in a way that is easy to observe. Because again, internal energy, what we're in essence saying is how much energy does a substance have? How much energy does a reaction contain? How much energy is in that piece of wood, sake of argument? And so if you ask me, well, how would you go about measuring it? My first response would be, I really don't know. Again, it's not like I can put a thermometer into it and get some type of information from that. So when we talk about internal energy, what we usually refer to as internal energy are 2 factors that come together. One is this idea of Q, better known as how much heat does the object or reaction or system possess. And then W is how much work does the system, the reaction, the object possess, right? And so when we add up the amount of heat plus the amount of work, then that gives us overall the amount of energy or internal energy that that system, object, or reaction contains. Now you might be listening to all of this and going, but that makes no sense. How can I measure the amount of work in an object or the amount of heat in an object? And I would say you're right. There is no direct way to measure internal energy. So instead of measuring an actual value of internal energy, what we typically do is we measure changes in internal energy. And instead of writing this as E equals Q plus W, what you will often see it written as is what we have down here as delta E equals the change in heat energy plus the change in work. Okay, now we're going to take a few seconds to break that down because that sounds a little weird. When we talk about change in heat, that's probably the easier of the two to understand, because when a system gains heat energy, again, it's incoming, right? We could say that that system has undergone an endothermic process. Right? Likewise, a system or reaction or an object could give off heat. So for example, the match was burning, the firework went kaboom, right? Any of those possibilities brings us back to this idea of change in heat. In both of those instances, we would say that it was an exothermic process. Now, what we mean by this delta Q is that in essence, we can have a change in heat energy that is positive, endothermic, or we could have a change in heat energy that is negative, exothermic. An object can gain heat, an object can release heat. A reaction can gain heat, a reaction can release heat. That one is pretty straightforward. But the second one is the one that always throws everyone for a loop. What do you mean by change in work? And especially, how on earth are we going to relate this to chemistry? So first, let's talk about what we mean by change in work, and then we'll take it to the next level and relate it back to the chemical universe. So let us suppose that you are currently, right now, sitting down at a table and you're on the first floor of a particular building. If I were to take your chair that you're sitting on and I were to drag you to the elevator, put you in the elevator, hit the second floor button, right? You would rise up to the second floor. I come get you, and now I drag you to another table, right? Then in theory, your overall internal energy has gone up. Well, why is that? Assuming for a moment, let's pretend that you neither released or absorbed heat. Not true, but let's pretend. Why would your internal energy have gone up? Well, because I and the elevator just did all of this work onto you. I gave you some of my work. And so in doing that, what that means is that my delta W, my change in work, was positive. When a system, when a reaction, when an object has work done on it, then that reaction, object, process has a positive change in work. Well, what if, let's say, sake of argument, we now turn the tables. And now let's say that you were on the first floor and you decided to pick me up, walk me to the elevator, press the second floor button, carry me up to the second floor, and then put me in a new chair. Well, in that case, I bet when you finish all of that, you might be a little tired. Well, why are you tired? Well, you're probably tired because look at how much energy you expended. Let's say it a different way. Look at how much work you did. Now, when you do work, that means that you release work or you release energy, and so therefore delta W is going to be negative. So this is when I combine the amount of heat absorbed or gained by an object, a reaction, or a substance with the amount of work that was done to it or by it, right? When I add those two things up, that gives me my change in internal energy. And I can measure changes in internal energy, because then what I'm doing is assuming the first law of thermodynamics. Since energy cannot be created or destroyed, I can observe how it gets transferred between, let's say, the system and the surroundings, or one object and another object, one process and another process. Okay, so this is when we talk about changes in internal energy, this is often what we're dealing with. So now the million-dollar question is, well, I understood that whole work example, but how does a firecracker or a match burning, right, do work, quote unquote? How does a reaction do work? And so in order to answer this question, we have to understand a new concept known as pressure volume work. In chemistry, work done to or work done by a reaction is referred to as pressure volume work. Mathematically, it looks like what I've written there in yellow. So the change in work equals negative, we'll talk about that in a moment, pressure times a change in volume. Now, you're probably sitting there saying, okay, you totally lost me. What does that mean? And so in order to help us out, I'm going to use my, again, amazing artistic ability. And we're going to look at this idea that I have here that's known as a piston. And so here's what happens. Let's pretend for a moment that we're inside your car's engine, and we're looking at one of the typical pistons that's in there. Understand that your car works because as the gasoline in your car goes kaboom, right? It causes the piston to shoot up, right? But let's get a little bit more into the details here. In reality, what we're saying is that in your car, what will happen is that gasoline gets placed inside of the cylinder, right? So a certain amount of gasoline gets in there. At some point, the spark plug at the bottom ignites, that gives it the activation energy, and as soon as that happens, kaboom! And the gas that was inside of that cylinder or inside of that piston begins to expand. So let's put it a different way. Let's suppose that I had sitting on top of this piston a small weight. Okay, so for the sake of argument, let's pretend that this represents my little weight that I have on top of my piston. When the gasoline gets combusted, we're going to push that weight upwards. Now let's stop and think about that. What is work? Work is force being moved through a distance. Force times distance. If the mass is sitting on top of that piston, weighing down that piston, that mass exerts a force. And so what had to happen? The gas had to exert a greater force, and in doing so, raises the level of the piston. It actually causes the piston to go from its initial position all the way up to there. So there's actually a change in height. Now, because all of this is happening three-dimensionally, the better way to say this would be as follows. Initially, my piston had an initial volume. The substance inside ignited, and we ended up with a final volume. The change in volume becomes my delta V. And so what happens is that it is becoming very apparent to me that work was done when a gas that had a certain pressure, we'll speak more on that later, caused the piston or caused that gas to expand by a certain volume. And so this change in volume, the greater the change in volume, the greater the change in work. Now, what I've written here is not what I had a moment ago. What's missing is I did not add to this equation the negative sign. So let's take a look at why that negative sign is critical. In order to do that, let's kind of go back a second. Let me get rid of some of these. And let's see what's happening without getting into the math. I had a reaction. Sake of argument, let's suppose that I had one we've seen before, some propane, so C3H8, that I put into the cylinder and I combusted it. So it went kaboom with its 5 oxygens, it produced 3 CO2, and it produced 4 H2O. Right? Now again, the carbon dioxide and the water, both of those are gases. I'm making more gases than I started off with. So what happens? It goes kaboom. The gases push on the piston. They cause the piston to move upwards. The volume expands. So if we focus on my original propane and I go, hey, did this propane do work, or did the propane have work done on it? You would probably say the propane did work. It pushed, right? And so if it did work, then in my head, that means when I do work, I lose work. I go down in work because I just gave it to something else. And so if I'm doing work, I know on some level this has to be negative change in work, right? I know it has to be a negative change in work. The reaction did work on something. So now let's come back up here to this equation. Right now, if I look at this, when I see delta V is nothing more than final minus initial. Well, in this picture, it seems to me like my final volume is a larger value than the initial volume. And if my final volume is larger than the initial volume, then delta V is going to be positive. And if delta V ends up being positive, and pressure is already going to be a positive value, then I end up with a change in work that is positive, even though I know that the reaction actually did work. So mathematically, in order to avoid any of that confusion, this is why we stick the negative sign in front of the P delta V. And this is what we refer to as pressure volume work. And so when we put all this back into our original change in internal energy equation, what we find then is that the change in internal energy for chemistry is going to be the change in heat that a reaction underwent minus whatever the P delta V work that it did was. And this is how we relate internal energy to our chemical universe. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.